Hello, good afternoon to all of you. I hope all of you are doing well. So, in today's class, we are going to discuss the concept of timing diagram. Now, timing diagram is a graphical representation that represents the status or the condition of the various signals, whether the signals are high or low whenever a machine cycle is getting executed. Now, without the knowledge of a timing diagram, it becomes very difficult for one to match the peripheral devices to the microprocessor. Now, timing diagram also represents the execution time taken by each of the instruction in graphical format, and it's represented in T state. Now, before moving further, let us acquaint ourselves to a few important terminologies. Now, the terminologies are instruction cycle. Assume that the microprocessor is executing an instruction. Then instruction cycle is the time taken to complete the execution of the instruction by the microprocessor, right? So, instruction cycle is the time taken to complete the execution of an instruction by the microprocessor. Now, an instruction cycle consists of 1 to 6 machine cycles. Now let us try to understand what is a machine cycle. Now machine cycle is the time required to access the memory or IO devices. I'll further repeat it. Machine cycle is the time required to access the memory or the IO devices. Or it may also be defined as the time required to complete one operation of accessing memory or IO devices. It also represents the time required to complete one operation of acknowledging an external request. Now, one machine cycle may consist of 3 to 60 states. Now, let us try to further understand what is a T state. Now, T state, the machine cycle and instruction cycle takes multiple clock periods. Again, I'll repeat it. A machine cycle or an instruction cycle takes multiple clock periods. Now, a portion of operation carried out in one system clock period is called as T state. Again, I'll repeat it. A portion of an operation carried out in one system clock period is called as T state. Or T state may also be alternatively defined as T state is one subdivision of the operation performed in one clock period. Now, each instruction of 8085 consists of 1 to 5 machine cycle. Again, I'll repeat it. Each instruction of 8085 consists of 1 to 5 machine cycle. Whenever 8085 processor executes an instruction, it tries to execute the machine cycles in some predefined sequence or in some specific order. Now, the processor takes a definite amount of time to execute the machine cycle, and the time taken by the processor to execute a machine cycle is expressed in T state, as we have already discussed. So, one T state is equals to the period of the time period of the internal clock signal of the microprocessor. Again, I'll repeat it. One T state is equal to the time period of the internal clock signal of the microprocessor. Now, T state starts from one falling edge and terminates at the next falling edge. So now let us uh, try to simplify it. So instruction cycle consists of multiple machine cycles, whereas a machine cycle consists of multiple T states. Now, a T state is defined as a time period. A time period or T state is defined as 1 by f, where f is the internal clock frequency. Now let us try to understand timing diagram for the various signals. Now the first signal that we need to understand is address latch enable. Now address latch enable, as we've previously learned, is an active high signal. So it is activated during the beginning of T1 state of each machine cycle, and it remains active till the T1 state. Now, the purpose of address latch enable is to enable the multiplexed address data line to work as address lines. So there are 8 multiplex address data lines starting from AD0 to AD7. So address latch enable, whenever latch is enabled at T1 state, then AD0 to AD7 will function as A0 to A7. Now, that is the utility of address latch enable. So address latch enable, again I'll repeat it, it is an active high signal. It is activated during the T1 state of the machine cycle, and it will remain active till the T1 state, and it enables the address multiplex data lines to be used as address lines in the T1 state of the machine cycle. Now likewise, the next signal that we have, so this is, you see, this is the graphical representation of ALE. So ALE becomes active in the T1 state of the machine cycle, just to enable the multiplex address data line to hold address. Now data bus. Now data bus, they're using the data bus. So data bus, we have multiplex address data lines AD0 to AD7. So at certain instance of time, it is used as A0 to A7. At certain instance of time, it is used as D0 to D7. Now, using the data bus, that is D0 to D7, there are two types of data flow which are possible. That is, whether the data is flowing from the memory to the microprocessor or from the microprocessor to the memory. Okay, again I'll repeat it. Using the data bus, there are two types of flows that are possible. That is, whether the data is transferred from the memory to the microprocessor or from the microprocessor to the memory. Now, the data transfer happens during the T2 and T3 state. Okay. Always remember, the data transfer happens during the T2 and T3 state, because in the T1 state, AD0 to AD7 will act as A0 to A7. Now there are two cycles, as I've already said. So one is the read machine cycle and the other is write machine cycle. In read machine cycle, the data will appear during the latter half of T2 state, while in write machine cycle, data will appear at the beginning of the T2 state. Again, you see, this is a very important thing that you need to understand. So there are two cycles that can be performed using D0 to D7. So one is read machine cycle, and the other one is write machine cycle. In read machine cycle, the data will appear during the latter part of T2, while in write machine cycle, data will appear at the beginning of T2. Now, read machine cycle basically means you are reading bytes from the memory, okay, or you are reading a byte from the memory or IO device, and write machine cycle basically means you are writing a data byte to memory or IO device. Now, here it is stated that in read machine cycle, data will appear in the latter part of T2 is because whenever you are performing a read operation, first what we need to do is we need to locate the specific location from where the data is to be read. Whether it may be in memory or whether it may be in IO, what we need to do is we need to locate the space from where the data is to be read. Now that will take considerable amount of time. Now that is called as an access time. Okay, again I'll repeat it. In order to read data from memory or IO, first what we need to do is we need to locate the location, and then we need to read. So in order to locate the location from where the data is to be read, it takes considerable amount of time. Now this is called as the access time. So what we have is we have certain amount of time required to access the value, and then what we can do is we can perform read operation. So here, as it's stated that in read machine cycle, data will appear only in the latter half of T2. Now, likewise, whenever you're performing a write machine cycle, so whenever you're writing data into memory or IO, the data is already available in the register. So simply what you need to do is you need to place into the data line. So here, what we do not require is we do not require any access time. So that is the reason why in write machine cycle, the data will appear on at the beginning of the T2 state. So this is one of the major distinction between read machine cycle and write machine cycle. In case of read machine cycle, since data, in order to access the data, we need certain amount of time, that's called as access time. So the data will appear at the latter half of T2, while in case of write machine cycle, data is already available in the register. It has to be just put to the data line. So data will appear at the beginning of the T2 state. Now, this is very much important for you to understand. So just see it is specified in the next point. But for reading a data from memory or IO device, first we need to select the required device. After selecting the device, the required data is to be read in take that's to be read is to be taken from the selected location and placed on the data bus. So a certain amount of time is required to perform this action. Now this is called as the access time. So in order to locate the space from where the data is to be read, so what we need to do is we need to spare a certain amount of time. So this is called as the access time. But as specified in the next point, in the write machine cycle, the access time is 0 because the data to be written is already present in the registers of the microprocessor, so it can be directly put to the data bus without any time delay. So this is very much important for you to know that in case of read machine cycle, you will be requiring certain amount of access time, and in case of write machine cycle, we will not be requiring access time because the data is already available. So this is one important aspect that you need to remember because this is required whenever you will be drawing timing diagrams for various instructions. Now let us consider the lower byte address. So as I've said that 80 to 87, these are time multiplex address data lines. So at certain point in time it acts as D0 to D7. At certain point in time it acts as A0 to A7. So 80 to 87 will act as A0 to A7 in the T1 state of the machine cycle. Okay, always remember A0 80 to 87 will act as A0 to A7 in the T1 state of the machine cycle to hold the lower byte of the address. So just see, it is written the lower byte of the address is available on the time multiplex address data line during the T1 state of the machine cycle, except in the bus idle machine cycle. Now likewise, you have higher byte address, that is A8 to A15. Now, just see, this is a representation of the A0 to A7, right? Now, higher byte address, that is A8 to A15. Now, higher byte address is available. Address is available in A8 to A15 for T1, T2, and T3 state of each of the machine cycle except the bus idle machine cycle. So always remember that A8 to A15 is capable of holding the higher byte of the address. So since it's not used for any other purpose, so what we can do is we can allow it to hold the higher byte of the address in T1, T2, and T3 state. So this is very much important. So now again what I want you to do is I want you to revise that what we have is we have D0 to D7 being used as AD0 to AD7 being used as D0 to D7 in the T2 and the T3 state of the machine cycle, where you have AD0 to AD7 being used as A0 to A7 in the T1 state of the machine cycle. So these things are very much important because you will be requiring this whenever you will be drawing the timing diagram for various instruction. Now let us move on to the signals, the status signals. We have IO oblique M bar, S0 and S1. Now as we have discussed in the previous class, now IO oblique M bar basically represents whether you're performing IO operation or memory operation. So whenever this particular signal is 1, it implies that you're performing IO operation, and whenever this particular signal is 0, it implies you're performing memory operation. Again, I'll repeat it. Whenever this particular signal is 1, it implies that you're performing IO operation, and whenever this signal is 0, it implies you're performing memory operation. Now S0, S1 or S1 or S0, again this is a status signal that is used to differentiate between whether it's a halt, whether it's a read, whether it's a write, or whether it's a fetch operation. So this we have discussed in the previous class. So we build up a table. So whenever both the values of S1 and S0, so S1 and S0 are 0, it means halt. Whenever the values of S1 and S0 is 0 and 1, it implies you're performing write. If whenever the value of S1 and S0 is 1, 0, you're performing read. And whenever it's 1, 1, you're performing fetch. Right? So just see, this is very much important for you to remember. Now, the status signal decides the type of machine cycle to be executed. So, what kind of machine cycle you're executing is decided upon by the status signal. So, that's why the status signal remains activated from T1 state of the particular machine cycle and will remain till the end of the machine cycle, because IO oblique M bar S0 and S1 dictates the type of machine cycle to be executed. So it will be activated from the beginning of T1 state of the machine cycle to the end of the machine cycle. So this is very much important for you to remember. Okay, right? So whenever you're performing opcode fetch, so when opcode fetch, right? Okay, so if you're performing opcode fetch, so if the opcode is stored in the memory, so the signal IO oblique M bar will be 0, right? Okay, and fetch, so S1 and S0 and S1 will both be 1 1. So as represented in the diagram here, so you see this is opcode fetch machine cycle. So in opcode fetch machine cycle, since the opcode pertaining to an instruction is stored in the memory, so it's a memory operation, so it will be 0, and S0 and S1. So since it's a fetch operation, the values of the signals will be 1 1. So this is the way how the signals are represented. So this is very much important for you to remember. So IO oblique M bar, S0 and S1 plays a very important role in deciding what kind of machine cycles you are executing. Now likewise, we have read and write. Now read and write signals decides the data transfer. So read basically means you are reading, the microprocessor is reading the data from the memory or IO device. Write means the microprocessor is writing data to memory or IO device. So read and write signal basically decides the direction of the data transfer. So whenever, so these are active low signals. So read and write both are active low signals. Now, whenever read is activated, right? Whenever read is activated, the data is transmitted from memory or IO devices or any of the peripheral device to the microprocessor. Now, again, I'll repeat it. So, whenever read is activated, the data is transmitted from the memory or IO devices or any of the peripheral devices to the microprocessor. Likewise, whenever write is activated, data is transmitted from the microprocessor to memory or any of the peripheral devices. This is a very important thing that you need to remember. So read and write signal basically decides the direction of the data transfer. So read basically means data will be transmitted from the memory or IO device to the microprocessor, and write means data will be transmitted from the microprocessor to the memory or the peripheral devices. Now, there might be a question that whether both the cycles are possible at the same time. Now, this is very true. So the answer is no. So these signals cannot become active at the same time. That is, both cannot take place at the same time. Now, as I've said that the data transfer, whenever you're performing read or write, the data transfer takes place at the T2 and the T3 state of the machine cycle. So read and write will be activated during the T2 and T3 state of the machine cycle. So this is very much important. Now just see, this is a very simple representation of read. So whenever you're performing read, so read is activated. Whenever you're performing write, write is activated. So in today's class, what we have learned about is, we have learned about what is a timing diagram. We have learned about what is the instruction cycle. We have learned about machine cycle. We have learned about T-state. We have learned about how to estimate the T-state. We have learned about the various signals that will be participating in realizing a machine cycle. Okay, right? So we have learned about address latch enable. We have learned about D0 to D7, then A0 to A7, right? Then A8 to A15, then the status signals IO oblique M bar, S0, S1, and read and write. So in next class, what we'll be learning about is we'll be learning about the timing, the various timing diagrams, and we'll take few examples and we'll try to understand it further. Thank you very much.